we should take a look at how you calculate this thing, now that we have a grip on its general behavior. So then we need some data, we need some numbers to work with.
Data!
This is the data that Cervantes collected. 9 participants, as I told you, and we can see how many musicians were playing for them, as well as how many orders they completed. Honestly, the correlation is a bit of a pain in the bums to compute. It's a lot of work, so at some point you want to leave this all this effort to a computer. That's what we will be doing. That's what many of you will be doing in the future at some point. So, but still, it's good to be aware of what computers do for us. After all, computers should not be a stand-in for understanding what we are doing. It's not like, oh, we just click through a few menus and that should take care of things. No, we want to understand what calculations we are doing so that we can critically evaluate them and to see if they make sense. What I need then is a number of things. There are a few steps that we go through when we calculate a correlation coefficient. There are also multiple methods, and I will actually walk you through 2 different methods. There's a most common method, you could say, that goes on the basis of cross products. And at some point we will also calculate the correlation based on z-scores. I'll explain why in a minute, but what we need to see first of all is how far every participant deviated from the mean on both variables. This will prove to be a key thing that a correlation wants to know from the data. How far does every individual score deviate from the mean? A bit annoyingly, you can see that PowerPoint is not so great at putting bars above an X or bars above a Y. So if you see a tiny dot above an X, that was supposed to be a nice long horizontal bar. In other words, the mean of X. So for example, for the first subject, they had only a single musician to listen to, whereas the average was 5. We take therefore 1 minus 5, and this gives us minus 4. And we will do that for all participants in the sample. It takes a while, but yeah. Of course, a computer can do this in a few milliseconds. Did you bring calculators to play along, or are you just like, yeah, I will sit back and relax to see where this ends? Up to you. Whoever is watching the video is, I always recommend calculating along to confirm what I'm doing and to also feel part of the process. It's very good for the experience and for your learning. We do the same thing for the orders. So again, you could say, the first completed 5 orders during his work shift, and that compared to the average was not very much. It was actually 4 less than what the average cook managed to produce. And so we do this for every individual again. The next step is to multiply those deviations from the mean by one another. So you multiply for the first person the minus 4 that they had. They were minus 4 below the mean on the first variable, and then they were also 4 below the mean on the second variable. We multiply those deviations in order to get what is known as a cross product. As in you basically make this product for every participant, and that leads to a number of multiplications. I will show you in a second what the sense is behind this, but there is a very good reason for multiplying for every person how much they deviate on one variable and multiplying that by how much they deviate from the mean on the other variable. So you have 9 different cross products in this instance. Let's take a minute to see why that is a logical thing to do. Here's the scatter plot again. This time I have indicated the 2 means using a horizontal and a vertical bar. So you can see the average number of musicians being 5, the average number of orders completed being 9, and the table on the left then uses color code to tell if a person was above or below the mean on that particular variable. Take a look at the last person, for example, in the list, final participant. You can see that they listened to more musicians than the average cook, and they were also more productive than the average cook. In other words, they were above the mean on both variables. This leads them to be in the upper right quadrant of the scatter plot. And when you think about it, so that's a person who scores higher than the mean person on one variable, and also higher on the mean than other persons on the other variable as well. Sounds like such people would contribute to a positive relationship, right? Higher than the mean on one variable, then also higher on the mean on another variable. And when you think about it, such people will have a positive cross product, because you multiply a positive deviation, on one variable with another positive deviation on the other variable. The cross product of this last participant is 10, so they will contribute to a positive correlation. The same goes for everybody who is in the upper right quadrant. Likewise, take a minute to observe some participants in the lower left quadrant. They scored below the mean on both variables, listened to fewer musicians than average, also completed fewer orders than average. That also should contribute to a positive trend, wouldn't you agree? Because that's like everybody who, you could even imagine it as, you would even be able to draw something like an upward line from the lower left quadrant to the upper right quadrant. So everybody who is in one of those two quadrants should actually make the correlation more positive. And the thing is that if you score below the mean on both variables, well, what does that mean for your cross product? Do you see it? If you look at the first participant, for instance.
It's positive?
Yeah, because you multiply two negative deviations by one another. Minus times minus gives us plus, and therefore such an individual will also make the correlation more positive. How about a few others? You have a few individuals who are not in the lower right, nor in the lower left, nor in the upper right quadrant, such as the person in the top left. That's actually one of the more productive cooks. They listened to fewer musicians than average, but completed more orders than average. That's kind of going in the opposite direction then, right? Participants like this should make the correlation more negative. And they do. Because who is this exactly? It would be the person in the fourth row, fourth person. 3 musicians but 12 orders. And you can see their deviation from the mean on X is negative, their deviation from the mean on Y is positive, and that leads to a negative cross product of -6. You can say the same thing of persons who are in the lower right quadrant. More musicians than average, less productivity than average, so they should also make the correlation more negative. Finally, you could notice this one individual who is directly on the border of 2 quadrants. What do you think they will do? Have you noticed it already? What if someone just is equal to the mean on one of the variables?
They will not affect the correlation.
Yeah, they will basically have a cross product of 0. They neutralize the correlation, you could say. They make it come closer to 0 in the end. Because this person does not deviate from the mean at all on musicians specifically, and that means you multiply 0 by -3. That does nothing. So that person will make the correlation veer more closely towards 0. Those are all necessary preparations for a correlation coefficient, but you will see that we are now 3/4 of the way. there are 2 steps left. Step 1 was to figure out all these cross products for all individual participants. This would obviously the largest amount of work if you do this all by hand. And the second step would be to make the average. Take the average cross product. This is also known as the covariance in many books on statistics. So it would imply that we add up all these cross products that we have, and then we divide them by n minus 1. Well, n is the total number of participants. You might be wondering, why do we not divide simply by n? That is a bit of a technical detail that I should not try to bother you with at this point. It has to do with the fact that we are dealing with a sample. Small correction, so to say. But I encourage you to see here that we are taking the average. So you would have to add up all the cross products that we have just calculated and then divide them by n minus 1 to get the average cross product. This is, takes a minute, but it leads to the covariance between musicians and orders. Right now it's a very neat number again, it's just 7. It's always helpful to pause the video real quick if you want a moment to consider what I've just said. Or if you want to rewatch a little bit to complete your notes. And I see we have a question from the audience, Konstantinos.
Maybe you will probably answer it later, but I wanted to understand how to interpret the number.
Yes. The covariance is already a fairly useful measure of how 2 variables are related. But your question is useful because it is exactly the kind of criticism you could have towards the covariance. It's still very hard to interpret. And the result is that is because it still depends on the scale of the variables that you used. I mean, what is 7 exactly? I wouldn't know. It's surely a positive relationship because it's larger than 0. But it's hard to tell if this is very impressive, whether this means that there's a strong relationship between one variable and the other. And that is then why we take the final step to standardize the covariance, to turn it into a number between -1 and +1, for which we can then use particular guidelines. The last step is that is exactly the correlation. To standardize the covariance, actually standardizing it to a z-score, of which I could say another number of things. But it basically means that we divide the covariance by the standard deviation of each variable. Assuming that you have also calculated the standard deviation before, or that you let a computer do at least this little part of the job, well, little part, standard deviation is at least equally annoying to calculate, by hand at least, then we would divide the covariance by the product of the 2 standard deviations, and that leads us to a correlation of 0.61. You could ask, is that impressive? Is that not a lot? It depends a lot on the field, honestly. On the scientific field. In psychological studies, this would already be quite a lot. Most relationships in psychology are small to medium in strength. And then you might ask, what is small or what is medium? Well, these are the guidelines put forward by Jacob Cohen, an influential statistician who mostly published stuff in the 80s, if I'm not mistaken. But I'm a bit out of my league here. A correlation of minus 0.1 or plus 0.1 can count as a rather light relationship. If we can really talk about cause and effect, then we would say this is a small effect. 0.30 counts as a medium relationship, and 0.50 is considered strong. As such, the correlation that we have found, 0.61, looks very impressive. unrealistically impressive even. You would start thinking that somebody made this all up. Yeah, but that's just what it is. 0.61 is our correlation, and that means that we might have a double winner on our hands. Because what did we say again? Yes. Still 0.62. And yeah, voilà, 0.6. Okay, then we might need to divide this thing into two halves, or I should look at the more precise number. I think the precise number is 0.606. But well, you both guessed at 2 decimal places, so we'll make this work somehow. Congratulations.